to this e-lecture. My name is Shruti Gupta and I'm working as an area geophysicist at Western Geco Schlumberger. Today I'm going to present a case study from North Sea which focuses on the recent advancements in full waveform inversion and its efficient integration with reflection tomography to not only achieve a good imaging solution but to also facilitate an overall reduction in project turnaround time. In this talk, I'll start with a quick introduction of the survey and some of the geological and the geophysical challenges associated with this area. This will be followed by a brief discussion on the optimized model building strategy that was implemented to resolve those challenges using full waveform inversion and multi-layer tomographic updates. Starting with the survey overview and challenges. Angelina survey is located in the Danish sector of the North Sea as highlighted in the map here. The water depths here are quite shallow, around 50 to 70 meters. The dataset that we used for this study was acquired in 2007 as 3D narrow azimuth data. The survey size is around 1450 square kilometers with a maximum offset of 6 kilometers. This was primarily a reprocessing project with the key objective of improving the imaging of the area. As per the geology, the dominant structural style of this area is the late Jurassic rifting modified by the compression and the inversion tectonics. There are several channel systems that are preserved in upper 500 meter of the strata and as can be seen from the depth slice here, these channels vary from the simple linear systems to more incised sinus systems. To further add to the complexities related to imaging, we have presence of chalk and faults as shown in the seismic section here. So let's see how these translate to the geophysical challenges. The presence of small-scale low-velocity channels, if not resolved in the model building stage, can cause significant distortion of the underlying events, and as highlighted in the seismic image here. And as it is a shallow water environment, we have limited sampling of the offsets and reflection angles in the data, which makes it quite difficult for the reflection tomography to resolve. So the approaches that have been traditionally applied to resolve these sort of challenges are structurally constrained tomography or some sort of interpretive methods. There was a previous processing of a nearby survey in this area, and interpretive method was implemented to resolve these challenges, which basically involves interpreting these channels, scanning for the velocities in them, and updating into the model. However, there are some problems associated with this approach. First being, the compensation is quite localized and aims at mostly big channels. Further, if you look at the velocity overlay on the seismic section here, it's quite straightforward to interpret the sides of the channel, but it's very difficult to delineate the base as we are kind of interpreting on the incorrectly imaged dataset. So we do require some sort of an iterative approach to resolve this, which could end up being very time consuming. With numerous examples published in the past few years, FWI is increasingly becoming a standard tool for resolving these sort of overburden complexities in the shallow water surveys. And as it is a data-driven two-way wave equation method, it can overcome the limitations of the array-based model building tools. It can automatically detect the velocity contrast with minimum manual interpretation, and to further add to that, this detailed high-resolution velocity model can be used as a separate attribute which can help in shallow characterization or geohazard analysis. However, conventional FWI also face some challenges based on the quality of the starting model or the missing low frequencies in the data, and therefore is quite prone to cycle skipping when the initial model has large kinematic errors. So let's look at how to mitigate this problem. The conventional least-squares FWI will update the model based on the direct subtraction between the observed and the model dataset. So if the time difference between the two datasets is not within half the cycle, then we are essentially subtracting the wrong events and hence it is cycle skipped. However, with the recently published adjusted full waveform inversion, instead of directly subtracting the observed and the synthetic events, we search for the displacement error between these two and then update the model based on these errors. And thus it helps to mitigate the cycle skipping and correct for the big background errors in the model. This method is very useful in the cases where we don't have a good legacy velocity available, or even for the old acquisitions where we usually have low frequencies missing in the data or we have poor signal to noise ratio. For this case study, as we didn't have a good model to start with or even the time velocities available when we started this project, we thought of taking the advantage of adjusted full waveform inversion. So we started with a very simple model that was kind of derived by the extrapolating of velocities from the nearby surveys. And as you can see, the model is quite simple and smooth. If you look at the observed versus model shot panel here, you can see that the data set is completely cycle skipped. In the next few slides, I'll present a model building strategy that was implemented using this initial model. Usually for the conventional model building workflow, if our initial model is quite off or if we have the missing low frequencies in the data, we have to wait for the d-multiple gathers to be ready so that we can perform a couple of iterations of tomography so that we can improve on our starting model for full waveform inversion. I just want to highlight here that the colors around the algorithm names have significance here. Blue means the good resolving power of that algorithm for that depth, and red means the low confidence. So after we have improved on our initial model with tomography, we run FWI, which mainly focuses on the overburden, and its penetration depth is constrained by the maximum offsets in the dataset. And hence we do need to run tomography post early arrival FWI to update the deeper sections and get our final updates. However, with the adjustive FWI, as it can deal with the inaccurate initial model and can correct for the big background velocity errors, we can start FWI as soon as we get the raw data that is parallel to the time processing workflow, which is then followed by few iterations of tomography to get the deep section update and hence our final model. And this is our optimized model building workflow. So compared to the tomography, FWI tomography workflow, this workflow helps us to achieve overall reduction in the project turnaround time. Let's look at a bit of details on the implementation of this workflow. To keep it efficient and cost effective, we just perform 2 bands of FWI updates at 6 Hz peak frequency to resolve the shallow up to 1000 meters, where basically tomography would really struggle. And then we perform the multilayer tomography with the explicit top chalk interpretation to maintain the strong velocity contrast of the chalk layer. Moving on to the results from the FWI updates. Here I have displayed an initial model overlaid on the initial stack, and the depth slice on the top of this slide shows the location of those inlines and crosslines. And as you can see, the model is quite simple. With the band 1 FWI update, we are improving on the background velocity trend and have started introducing the slowdown required by the channels just below the water bottom. With the band 2 FWI update, which very nicely puts the details in the models and delineates the shallow channels quite well. Another location, similar story. We have a very simple initial model. Band 1 adjustive FWI helps introducing the slowdown in the shallow channels, which is further delineated quite nicely with the band 2 least-squares update. Looking at the velocity overlays on the depth slice, I would just like to emphasize on the fact here that we are just 20 meters below the water bottom here, and we are able to capture the channels quite nicely. Another depth slice at 260 meter, and I want you to notice the complexities of the channel here and how FWI is picking up very small sinus channels and the fast cross-cutting of the slow and the fast channels, and this would have been very difficult for any other method to achieve. One of the common problems with the high-resolution update for the shallow water surveys is the leaking of the acquisition footprint into the velocity model update. There are few ways to address it. First, within FWI using the statistical sampling or increasing your gradient smoothing. In this project, we also looked at attenuating a post-full waveform inversion using some sort of statistical acquisition footprint attenuation method. And as you can see from the velocity depth slice here, the method has worked quite well and without any loss of resolution. Coming back to the observed versus model shot overlays, as I mentioned before, with the initial model, our data is completely cycle skipped. With the band 1 FWI model, we have improved on the background velocity errors and our match is improving. We've bordered within the half wavelength criteria, which is then followed by the band 2 FWI model, and we have a very good match after that. However, this is a very localized view of how our model update is performing. To QC the update globally, we generate a cross-correlation time-shift map between the observed and the model dataset for different offset ranges. As per the color scale here, green represents towards the zero time-shift error, which is the ideal case and where we want to be. while blue indicates the model is fast and requires slowdown, and red indicates it requires speed up. The presence of any structural information in these maps, such as channels in this case, indicates incorrect velocity for that particular event. With band 1 update, you can see the QCs are quite consistent, and we have improved on the background model trend and got the data within the half wavelength criteria, which is further improved with the band 2 update. Looking at the seismic itself, this is a Kirchhoff depth migrated image using our initial model, and I've highlighted few areas for you to focus on. With the FWI update, you can notice that the channels look more focused. There's a reduction in the undulations of the events underneath these channels, and even the fractured events below look clearer, sharper, and with a better stacking response. I'll flip it again, before, after. Now let's look at the gather flatness. This is a zoom view for the top 800 meters, and with the FWI update, the gathers look flatter even in the very shallow area. As I mentioned earlier, that the early arrival FWI has limitations in the depth of penetration, and to further keep it cost efficient, we concentrated only up to the 1000 meters for the FWI update where tomography would really struggle, and then this was followed by the multi-layer tomography to achieve the deeper updates. Before I delve into the results, let's briefly look at the multi-layer tomography method. In cases where there is a strong velocity contrast, such as presence of chalk, it's quite desirable to have sharpness of property boundaries to have accurate representation of the geological layering and be consistent with the borehole velocities. Multilayer tomography uses explicit boundaries inserted in the model and can account for the changes of the ray paths with the velocity change, and hence can update every zone in the model simultaneously. It also accounts for the movement of the boundaries after the velocity update. And as you can see with the well velocity overlay here, with the global tomography you get a smooth gradient, but with multi-layer tomography, we achieve that sharp property contrast as required. However, it does require the interpretation of the layers that needs to be inserted in the model. Looking at the results, here we have velocity input to the multi-layer tomography on the right and some well velocities overlay on the left. And with the velocity update, you can see that after the multi-layer tomography, the velocity is conforming quite well with the geology, and as shown with the red curve of the updated model on the well velocities overlay on the left, you can see we have been able to maintain the sharp velocity contrast that is quite consistent with the borehole information. Looking at the stacks and gathers, I've again highlighted some areas for you to focus on. And with the multi-layer tomographic update, you can see that the events look more focused, sharper, and continuous, and the gathers are looking much flatter. I'll flip again, before, after. And let's compare it with the results with what we actually started with. And you can see this is the data set with our initial model, and this is with the velocity update with full waveform inversion and multi-layer tomography. And it's quite evident that there's a significant improvement in the imaging here. So to conclude, adjusted full waveform inversion has proven to be a great tool that overcomes the half wavelength criteria. And it not only allows us to start FWI with a very simple initial model, it further extends its applicability to the vintage datasets with missing low frequencies in it. And if employed earlier in the processing workflow, parallel to the time processing, it can lead to the reduction in the overall project turnaround time. With this workflow, we have been able to efficiently capture and achieve high-resolution shallow channel updates, and by limiting the depth of the update with FWI and just concentrating in the area where tomography really struggles, we have been able to achieve a cost-effective solution. And last but not the least, the integration of FWI and multi-layer tomography provides a good solution which helps maintaining the sharp velocity contrasts that are quite consistent with the borehole information. Finally, I'd like to just acknowledge and thank Total E&P and Danish Underground Consortium for their permissions to publish this result, and our colleagues in Schlumberger for their contribution towards this work. Thank you for your attention. You can like and share this video, and for more e-lectures, take a look at the e-lecture playlist. Thank you.